Hello everyone, welcome to our presentation on the topic Efficient Online Testing for DNN-Enabled Systems using Surrogate-Assisted and Many Objective Optimization. I am Pitashulak and this work has been done in collaboration with Dr. Dongguan Chen and Professor Leonard Bryant. Let's start with the introduction. DNN-enabled systems, DADS, are those systems that are composed of multiple DNNs which are capable of performing different tasks, such as object tracking, object classification, traffic light detection, and traffic sign detection. For example, self-driving cars and autonomous drones. Both of these subjects have to travel from their initial point to their destination using different DNNs to avoid safety violations. Our goal is to test these DNN-enabled systems and find safety violations. There are two modes for testing such systems. First is offline testing, in which DNN is tested using pre-recorded data in an open loop mode. And the second is online testing, in which the DNN is embedded inside the application environment and it is tested in a closed loop mode. From the literature, we know that offline testing cannot find safety violation properly because it does not take into account the accumulation of error over time. So we can trust only online testing for finding safety violations. But online testing comes with its own set of challenges, such as there can be a large input space to be exhaustively explored. There can be many safety requirements to be considered at the same time, such as a vehicle should not collide with the pedestrian or a vehicle should abide by the traffic rules. And simulation is often computationally intensive, which means that running one simulation will require significant amount of budget. And often the DNNs are developed by third party, so we do not have access to the internal information of the DNN. To address these challenges, we propose SAMOTA, which is a surrogate-assisted many-objective testing approach. It is a combination of two distinct approaches. First is many-objective search to effectively achieve many independent objectives within a limited time budget. And the second is surrogate models that mimic the simulator while being computationally much less expensive. Furthermore, our approach is a black box approach, which means that it does not need any internal information of the DNN. This page presents the key ideas behind SAMOTA. We use two different modes of searches. First is global search, which is basically for exploration of the search space. And the second is local search, which is for the exploitation of the search space. Global search uses global surrogate models that are trained on all the data points from the database, while the local search uses local surrogate model, which is trained on the subset of the database. Both of the searches exchange information using a shared database. Briefly speaking, global search with global surrogate models first explore the search space by capturing the global outline of the fitness landscape, and then local search with local surrogate model exploits the promising regions found by the global search. But what are surrogate models? Surrogate models are used to replace the computationally expensive function evaluation with much less expensive approximations. Three of the most commonly used surrogate models are radial basis function, RBF. It is a type of forward feed artificial neural network comprising of three layers, namely the input layer, the hidden layer, and the output layer. Radial basis functions are used as activation function, and the output is the weighted sum of radial basis functions. Another most commonly used surrogate model is polynomial regression. It forms a relationship between the input and the output as an n-degree polynomial. Another most commonly used surrogate model is kringing, which is also known as Gaussian process regression. It is one of the most widely used surrogate models since the 1970s, and it predicts the value of a function as a combination of linear function using a stochastic process. Though many surrogate models have been studied, there is no single surrogate model that can perform consistently well for all the problems. To mitigate this issue, the ensemble of different surrogate models can be considered. The output of the ensemble is the weighted sum of the output from the individual surrogate model, and the weight is assigned based on the error of the individual surrogate model during the training phase. Using an ensemble has its own set of advantages, such as it is very easy to calculate the uncertainty. The higher the disagreement between different individual surrogate models, the higher will be the uncertainty, and vice versa. Due to weight assignment, it reduces the risk of a single poorly trained surrogate model, and it performs better than a single surrogate model. This page presents the overview of our surrogate-assisted many-objective test generation approach, SAMOTA. We start with initialization using the attributes from the domain model. We execute the simulator and build an initial database. This initial database is first used by global search. First, it trains the global surrogate model using all the data points in the database. Then the trained surrogate models are used by many objective search, which returns us the most critical test cases, which are for exploitation of the search space, and the most uncertain test cases, which are for the exploration of the search space. We execute these two sets of test cases on the simulator and update the database. The updated database is then used by local search. Local search first clusters the top n% data points and then train one local surrogate model per cluster. And then it executes single objective search algorithm on each cluster and find the most critical test cases, which are then again executed on the simulator, and the database is updated. And then we continue with global search and then local search till the end of search budget, and in the end we get the minimal test suite, which is a subset from our database. Note that the search is focused only on the uncovered objective, which therefore reduces the number of real simulation execution. Now let's go over a bit of detail regarding global search and local search. First, global search. Global search aims to explore the search space using global surrogate models only for uncovered objectives. These global surrogate models are trained on all the data points from the database. The trained global surrogate models are then used by many objective search algorithms to give us most critical and most uncertain test cases. Most critical test cases are for the exploitation of the search space, and most uncertain test cases are for the exploration of the search space. The degree of uncertainty can be measured according to the magnitude of disagreement among the output of the members of a global surrogate model. These uncertain test cases are of vital importance because they maximizes the information gain of the surrogate models, making them accurate faster. Both these set of test cases are executed on the simulator and the database is updated. Now moving on to the local search. Local search uses local surrogate model, which is constructed using the top n% data points from the database for each objective. We found an approach in the literature for the surrogate model generation that generates one surrogate model for top n%. But it is not optimal, as it can be seen in the figure that the top n% can be widespread and hence cause the surrogate model to lose its efficiency. To avoid this issue, we propose using a clustering algorithm to cluster the top n% data points and build one surrogate model for each cluster. Then we run single objective search algorithm on each cluster and find the most critical test cases. And these test cases are then executed on simulator and the database is updated. Basically, local search aims to exploit the promising areas found by global search using local surrogate models. For each promising area of each uncovered objective, it finds and it runs the best predicted test cases based on a single objective search. To evaluate our approach, we have formulated three research questions. The first research question is, what is the best configuration for local search? The objective of RQ1 is to find the best surrogate model generation technique and surrogate model for the local search. Note that we are only considering the best configuration for local search because from the literature we already have the answer for global search, that ensemble is the best configuration for global search. The second research question is, how do alternative approaches fare in terms of test effectiveness? The objective of RQ2 is to compare different approaches in terms of their effectiveness, and RQ3 is how do alternative approaches fare in terms of test efficiency. The objective of RQ3 is to compare different approaches in terms of their efficiency. For the case study subject, we use Pilot, which is a DNN-enabled automotive driving system. Pilot provides the implementation of state-of-the-art approaches based on pre-trained DNNs, such as it provides deep sort, which is deep, simple, online, and real-time tracking for obstacle tracking. It provides SSD, single-shot detector, for object detection, and for control, it provides model predictive control, or MPC. And for the simulator, we use Carla. Carla is an open source simulator based on Unreal Engine designed to support training, development, and validation of automotive driving systems. Furthermore, Carla provides handcrafted, high-fidelity virtual maps having various static environments such as different road types, different sizes of building, and different shapes of trees. This page shows the setup for RQ1 for finding the best configuration for local search. We have two different dimensions. First is the surrogate model generation approaches. We have two possible options. The first one is from the literature to generate one surrogate model for all top n% data points. And the second one is the one we propose to generate one surrogate model for each cluster generated using HDB scan. We use HDB scan to cluster the data points because we can provide a minimum number of data points in each cluster using HDB scan. And the second dimension is the surrogate model types. We have three possible options: RBF, polynomial regression, and crinking. Then we perform local search using genetic algorithm with the search budget of 2 hours, and we repeat it 20 times, and we measure the local search effectiveness, which is the maximum actual fitness score achieved when running all the test cases for each objective and averaging these scores across all the objectives. This page shows the result for RQ1. Let's first compare against the first dimension, which is the surrogate model generation approaches. We can see that our clustering-based approach for surrogate model generation is statistically significantly better than the existing approach in all the cases. And for the second dimension, which is individual surrogate model types, we can see that there is no statistically significant difference between different surrogate model types. And on average, we can see that RBF with clustering-based approach performs better than other surrogate model types. So we chose RBF with clustering-based approach as the configuration for local search in SAMOTA. Moving on to RQ2, which is the comparison of test effectiveness of the test suits generated by different search algorithms. For SAMOTA, we can provide an initial database to boost the performance of the SAMOTA by improving the accuracy of the surrogate model early. To better understand this, we use two different configurations of SAMOTA. One is with an initial database and one without the initial database. As alternative to SAMOTA, we use state-of-the-art many objective search algorithm tailored for test suit generation, SFITEST, and MOSA. And we also use random search with an archive as baseline. Using the algorithm from the set of search algorithms, we perform online testing of DADS with the search budget of 2 hours. We repeat it 20 times, and we measure the test effectiveness, which is the number of safety violations found by a test suit divided by total number of safety requirements. This page shows the results for RQ2. We can see that SAMOTA variants are statistically significantly more effective than other many objective search algorithms tailored for test suit generation and random search with archive. For RQ3, which is the comparison of test efficiency among different search algorithms, we use the same set of search algorithms as RQ2. We perform the online testing of DADS with the search budget of 2 hours, and we repeat it 20 times. And we measure the test effectiveness with the interval of 20 minutes. This page shows the result for RQ3. In the first 20 minutes, when the surrogate models are not well trained for SAMOTA-E, which is the variant of SAMOTA without an initial database, MOSA is performing better than SAMOTA. And as the process goes on, after 80 minutes, when the surrogate models are well trained for SAMOTA-E, both variants of SAMOTA perform better than other many objective search algorithms and random search, and keeps on performing better for the rest of search. We can say that SAMOTA is more efficient then alternative test suite generation approaches as soon as its surrogate models become sufficiently accurate. And an initial database can boost the efficiency of SAMOTA in the initial search space. An initial database can boost the efficiency of SAMOTA in the initial search space and allow it to surpass other techniques right from the start. To conclude, during this presentation, we present SAMOTA, which is a novel technique to efficiently and effectively generate test data for DNN-enabled systems in the context of online testing. We experimentally showed how to select the best configuration for local search. Furthermore, we also showed that SAMOTA is significantly more effective and more efficient than the state-of-the-art many objective search algorithms tailored for test suite generation. That is all from my side. Thank you very much for your attention. And if you have any questions, my contact details are on the slide. Please feel free to contact me.